other way, would you? I'm not kidding. I'm totally being facetious. Okay, well, let's get started here. We're going to take a look at this practice quiz. And this is just some questions that I chose from the ACS study guide. I thought it was a pretty good smattering of questions just to kind of review some of the concepts that you learned in Organic Chemistry 2 and Organic Chemistry 1. And something you want to remember is that, sometimes students will get intimidated when I'll say, well, the exam encompasses Organic 1 and Organic 2. But remember, you apply the concepts in Organic Chemistry 1 pretty much every day that you study Organic Chemistry 2. They never go away. So with that in mind, let's take a look at question number 1. It says, onto which of the numbered atoms in the following structure can the negative charge be moved by drawing resonance structures? So we have the negative charge right here. And something that you might have noticed, when you're doing resonance structures is that you can make some predictions about where you can put negative charges and things like that. But let's take a look at this one. Hold on. So let me just see. Yeah. Okay. I'm going to switch over to a blank document and I'm going to draw all the resonance structures that I can come up with for this thing. So just bear with me here. We're going to go over here and we'll give this the old college try. So let's see here. ACS practice quiz. And this is question 1. And so I'm going to redraw that aromatic compound and be very careful to draw it correctly here. So I have an aldehyde here. Then I have the phenoxide here. So there's my negative charge. And then I have another aldehyde over here. So 2 aldehydes. So let's get started. Put our open bracket and we'll start pushing some arrows. So I have an allylic double bond here. So let's draw that first resonance contributor. So we end up with something that looks like this. And you can see why scratch paper is necessary for an organic chemistry exam. I'd say it would be very difficult to do an exam without some scratch paper. So there's our first resonance contributor. Let's draw another one. So we're going to take a double bond here. We'll put the lone pair up here. And then we'll take a break and we'll kind of take stock of where the charge is. So we've got this. We've got our negative charge up here. There's our aldehyde. We've got our double bond. And there's the other aldehyde. So let's see. So far, we have had the charge at carbon number 6. So this is carbon number 6 here. This is the negative charge at carbon number 4. So we've eliminated A and D. So A is gone and D is gone because those only have 1, 3, 5, and 7. And we skipped those. They don't have any of 4 and 6. So that can't be it. So let's keep going from there. And we've got another allylic lone pair here. So let's draw a resonance charge there. So we're going to move these electrons over here. And then we end up with something that, oops, let me get my black pen here. We're going to end up with something that looks like this. So we're going to have double bond here and here. This. There's our aldehyde. There's this aldehyde. And then I've got my negative charge here. And you can see where this is going. So now I've got the charge at carbon number 2. And then you can clearly see that there's another resonance structure you could draw here where you put the lone pair here to make a double bond. You delocalize the electrons down on the oxygen, which is labeled 8. So let's do that. So we end up with a double bond here. You've got the negative charge down here, a double bond like this. And there's no way to get the negative charge up onto this oxygen. You cannot do that in this resonance structure. And so there you have it. So that is the atom that is labeled 8. So I'll get my blue pen. So we've got 2, 4, 6, and 8. We have all of those. So the answer must be C. And I would definitely think that you would need to use scratch paper to answer a question like that. And I think it would be very difficult to answer that without going to a piece of scratch paper and trying it. I suppose you could solve it in your mind, but I think that would be the best way to go. So let's go back to our practice quiz. We solved the first one. It's C. Let's take a look at number 2. Which of the indicated protons in this compound would have the smallest pKa value? Is anybody able to solve this one kind of quickly? And I'm not a speed guy. I'm not about racing through questions. But is there anybody who has an inkling about which one of these has the smallest pKa value in this compound? There's one that's... Sorry, go ahead.
Oh, it's probably A because there would be a lot of resonance structures that it would have.
So it can't be A because you can't have a vinylic lone pair, right? If you were to deprotonate that, right? I see you're in the right mindset, right? But you never are going to have anything like that. Okay, so that's a vinylic lone pair. So the pK of that proton, Caitlin, it's actually like, like 43 or something, which, any kind of sp2 hybridized carbon is going to have a pKa around 43. Then you have, something on, well, that's sp3, that's sp2 hybridized too. What am I talking about? So this is also around, or no, sorry, this one here, that one's on an sp3 hybridized carbon, so that's going to be around 50, maybe a little bit lower. We'll put here below 50 somewhere. But what about the terminal alkyne, right, Karen? Karen, do you remember, and I'm putting you on the spot here, and this could go to anybody. Does anybody remember what the pKa of a terminal alkyne was? The green.
Was it around 20 to 25?
Yeah, it's around 25. Exactly. So pKa is, we'll just put here around 25. So that, remember we did all kinds of deprotonation of these with sodium amide? The reason why is because that pKa of 25 means it's acidic enough that it can be pulled off, right? And so it's much more acidic than any other proton in here. Anything that's on an sp2 or an sp3 hybridized carbon, but this carbon that's a terminal alkyne sp hybridized has a pKa of around 25. All right, give me a thumb. Does that make sense to everybody now? Right, and we could even look at this from the point of view of Areo if you wanted to, right? ARIO. We can't use atom because if you were to make the conjugate base of any of these, the negative charge would be on a carbon. We can't use resonance because there's no, well, I guess there's no real resonance structures to draw. There's no induction. So we have to use orbital, right? And this is sp2. This is sp2. This is sp3. But this one, since it's sp, we know that the negative charge after that terminal alkyne is deprotonated produces an alkynide. And since an sp orbital is smaller than an sp2 or an sp3, it can better stabilize the negative charge. All right, cool. Let's move on from there. Oh boy, Newman projections. All right, so Newman projections. Question 3, it says, which Newman projection represents the most stable conformation of this compound? So I think the first thing we should do is try to draw the bond line structure of this compound. So we've got 2 methynes in the middle. Oops, where's my pen? You got 2 methynes, and they each have 2 methyls coming off of them. So you've literally got 2 methynes and then 2 methyls. So the compound is nothing more than 2,3-dimethyl butane. And what you're doing is you're looking down one end of this bond. Okay, going from here to here. Okay, that's all it is. So you're looking for the most stable Newman, or the most stable conformation, represented by a Newman projection here. First question, let's try a little process of elimination. Are there any of these Newman projections, and I'll give you a clue, there's a couple of them that are just like, no, that's impossible.
B and D, because it's not the same compound.
Yeah, absolutely, right, Caitlin, right? Because if you look at B has a tert butyl group on it here, and D has a tert butyl group on it. So neither of those, it's not even the same structure, is it? The A and C are both, they're both 2,3-dimethyl butane. However, one of them is more stable than the other. Could anybody guess? And I'm sure you all know. Between A and C, which one would be more stable, do you think? A or C?
C. So
C, right? C would be the more stable one, okay? Does anybody remember the Gauche interaction? Gauche interaction. If you look at A has a Gauche interaction here between those two methyls. Then it has a Gauche interaction between those two methyls. And it also has a Gauche interaction here. So we have 3 Gauche interactions. Whereas in C, yes, there are Gauche interactions. However, in C, there's only 1, 2. And so since C has less Gauche interactions, it only has 2. So put 2 Gauche interactions. It's more stable. Yeah, there we go. And that's really all there is to it with that one. You know, I think the main thing with this one is being able to suss out which structures, B and D, aren't even right. You know, and then maybe kind of take your time and figure out, well, which one is more stable? Is it A or is it C? All right. Let's see. Where's question number 4? Somewhere over here. Oh, here we go. Which resonance form best explains the greater acidity of para-nitrophenol relative to phenol? So if we compare phenol, so phenol is just this, okay? Phenol has a pKa of around 10. It's around 9.9, 10, something like that. And then it says, what if you've got para-nitrophenol? So para-nitrophenol, remember that a nitro is an electron withdrawing group, strongly electron withdrawing. So here's the Lewis structure of the nitro, like this. Now this is going to have a pKa that's less than 10, so it's more acidic. Why is it more acidic? It's because when you make the conjugate base of either of these, okay, they have resonance structures, right? The phenoxide, you could draw a resonance structure. You could draw this. You could put the negative charge here, here, or here. However, if you do the same thing with para-nitrophenol, you can have the negative charge here, 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 and here. You can delocalize it all the way down to the oxygen. So when you do that, like, what does that look like exactly? Let me just erase this for a second here. And what if we drew all the curved arrows that show the delocalization of those electrons all the way down to the oxygen? We're going to look something like this. And then the resonance structure, kind of running out of space here, but it's going to look something like this. So we've got our 6-membered ring, got our double bond like this, double bond to nitrogen. And then we have the 2 oxygens like this. So this explains why para-nitrophenol is so much more acidic than phenol. It's because you can delocalize that negative charge all the way down to the nitro. Does anybody remember what type of reaction we saw where we showed the delocalization of a negative charge down into a nitro group? So we would have seen this in an SNAR reaction in the chapter on electrophilic aromatic substitution and all that kind of stuff. Give me a thumbs up if that makes some sense to you. The negative charge being delocalized all the way down to the nitro. Yeah, okay, cool. Yeah, it's something that we saw in SNAR. So I think I have another question in here about SNAR, so we'll be sure to go over that again. Okay. Here we go. Let's take a look at some Kahn-Ingold pre-log rules. This is just a review of Organic Chemistry 1. Many of my students are interested in writing standardized exams, and so I would be remiss to leave something out with R and S in it. It says, which molecule has the R configuration? So if we start with A, we have our lowest priority group is in the back. This is our highest priority group, the oxygen. And you have a carbon here and a carbon here. Well, this carbon is attached to oxygen, oxygen, hydrogen, and this carbon is attached to 3 hydrogens, so obviously this one is the winner. So we have 2, then we have 3. We go from 1 to 2 to 3. That's going counterclockwise, and so this is S. If we go over to the next one, I'm going to have to erase some of this just to make some space for myself. Let's see here. The next one, we've got our hydrogen in the back. Oxygen is in the front. That's the highest priority. This carbon is attached to OOO, and this carbon is attached to OHH. So here's my tiebreaker. This is number 2. This is number 3. I go from 1 to 2 to 3 counterclockwise, and thus this is S. If I go to D, in D, let's see, the hydrogen is in the back. Oxygen is the highest priority. The nitrile is the second highest priority. 1, 2, 3. So we go like this. Hydrogen's in the back. So again, this is counterclockwise. It's S. So that brings us to C. And with C, you can see and see that the highest priority group is the oxygen. Then this carbon is attached to oxygen, oxygen, oxygen. And this one is attached to oxygen, hydrogen, hydrogen. This is my tiebreaker. Therefore, that's going to be the second highest group, and this is third. Notice that the lowest priority group is in back, but it's not a hydrogen. It's a methyl group, but that's okay. So now we have 1, 2, 3. We're going clockwise like this, and so the stereochemistry is R. So the answer is C. A little bit of review of Kahn-Ingold pre-log rules. So make sure you're able to designate stereocenters as R and S, because if there's a question on the exam that involves nomenclature of a ketone, it might have a chiral center in it. So you need to be able to identify that chiral center as R or S. I'll just throw this one out to my students who are all really good. What is the stereochemical classification of these two compounds? You've got 1S, 2S, 1,2-cyclohexane diol, and 1R2S. 1,2-cyclohexane diol. Could anybody tell me the definition? How would you describe these two? Enantiomers, diastereomers? Yeah, they're diastereomers, aren't they? Yeah, absolutely. Thank you. All right, and how did my students know that? So if you're confused, if you don't remember, let's just review quickly. All right, if you have 1S and 2S, to make the enantiomer, you have to switch both. You'd have to have 1R, 2R. Right? If you reverse every stereocenter, you get an enantiomer. However, if you only invert one of the stereocenters, so if you have 1R, 2S, which is what we're doing, since you're only inverting one, they're non-superimposable, but they're not mirror images. So non-superimposable, but also they are not mirror images. So they're not enantiomers, and therefore they're diastereomers. Anyhow, there we go. All right, great. Good. My students seem to be pretty good. Hey, let's try number 7. You guys remember cis trans isomerism? There's two kinds of cis trans isomerism. Could anybody describe one of the places we saw cis and trans in this class? You could either put it in the chat or yell at me. I don't care. Where would you see cis and trans? There are actually two places we saw cis and trans in organic chemistry. So one place would be in an alkene. Right? If you have an alkene, you can have this, that would be cis, and sorry, that's trans, my mistake. Mr. Dion needs some more coffee, I think. So this is trans. And then if you had your two X's on the same side, that's cis. But there is another place that we saw cis and trans in this class, and that would be in a ring. So let's say you have a 6-membered ring. If you have two groups on the same side, like this, they're cis to each other. However, if they're on opposite sides, so let's say you have X here and then you have Y here, X and X, then they're trans. So if we look at these questions, this one is an alkyne, and an alkyne has no cis or trans. So it can't be A. If we go to C and you draw the bond line structure of C, C is this, where you have a hydrogen and a chlorine, but then you've got two methyl groups here. And if you have two R groups that are the same on one of the carbons of the double bond, there's no cis or trans, And then in D, you have two double bonds on the same carbon. That's called an allyne. Oops. No, I think it's yellow. I haven't thought about allenes in a while. Anyhow, so those also have no cis or trans. No cis or trans. However, in B, you could draw this compound with both of the hydroxyls going up like this. They'd be cis. Or you could draw it so that one of the hydroxyls is going up and the other one's going down like that. And that would be trans. So the answer must be B, cis and trans. Okay, let's see here. Question number 8. Potential energy diagram of Newman projections. Okay, so we've got this diagram here. We have potential energy on the y-axis. We've got rotation on the x-axis, and you can see that we're going up high and down low. So my question to you is, we've got some maxima here that I'm highlighting in yellow, and then we have some minima that I'm highlighting in green. Okay, 0 and 360 are identical, but whatever. I'll just do it like that. What do the maxima represent? Do they represent staggered conformations or eclipsed conformations? The maxima in yellow, staggered or eclipsed?
Staggered.
Eclipse.
They would be eclipsed, right? Because staggered is when you have, oops, there's no black pen. Staggered would be something like this, where you have all the bonds as far away from each other as possible, like that. Okay, staggered. Whereas the maxima would be eclipsed. So that's when everything is eclipsing everything else. So kind of like this, like that, where they're blocking each other. Does that make sense? Eclipsed, like that.
Yeah,
So,
I just got them backwards.
Yeah, no worries, no problem at all. So if what I'm saying is true and everybody seems to agree with me, that means that we can cross off which ones. Which ones can we eliminate right away? So they're looking
C and
at
D.
point. Exactly. So we can eliminate C and D because we're looking for A. This is kind of confusing the way they lay out this question. They could have called it like point Y or something instead of naming it after. Anyhow, don't ask me why. But anyhow, we know that it's not one of the eclipsed, so we can eliminate A and B. So we can scratch both of those off. So it's got to be either C or D, but there's two types of staggered conformations, right? There's this one and this one. So the one that we're looking for is the one of these that's higher in energy. Would it be C or D?
D.
Absolutely, yeah, because in D, you have one gauche conformation. So this must, or one gauche interaction. So this must be the correct answer. And here, this, like if we were to call this, I don't know, let's just give it a letter. We'll call it Z. So this would be Z. This would be the lowest energy conformation you could possibly have. So the answer is D. All right, just a little bit about Newman projections. Newman projections are one of those things that just never go away. In organic chemistry, every time you think, oh, I won't see one of those today, it's like, blah. Okay, question number 9. I'll just throw this out there to my students. This is just kind of a little bit of terminology. What is the relationship between these two structures? The two compounds, two diols.
Constitutional isomers.
Yeah, I think so. How did you know that, Caitlin? Because they have the same what?
They have the same formula, molecular formula, but
Exactly.
different connectivity.
Exactly. Same molecular formula, but they have a different connectivity. That's what I would have said for the answer. And so they are just constitutional isomers, right? Nothing more than that. Same molecular formula, but they have a different way of putting them all, or putting the atoms together. I mean, you can clearly see this one is trans 1,2-cyclohexane diol, and this is cis 1,3-cyclohexane diol. So two different compounds, but same molecular formula. Question number 10. I wanted to show you this one because it's kind of interesting. It says, which reaction would proceed the fastest? What they're trying to show you here is that you're taking hydroxide in all 4 cases, and you're reacting it with something and basically doing what looks like an SN2. So, and why I say it looks like an SN2, because some of these wouldn't work. Okay, but it's like they're trying to show you an SN2 reaction. You know, but if you look at A, in order for this to happen, right, for this to attack here and for this to, I mean, there's no good leaving group here, right? A methoxide is not a good leaving group. A thiolate is a little better leaving group, but it's still not a great leaving group. Then you've got an amide, right? A nitrogen with a negative charge, which is a horrible leaving group. Does anybody recognize this? And you probably would have had to look at this beforehand. Does anybody recognize this part that I'm circling in red here? What they're showing here, when it says C6H4, they're trying to show you this. It's this. You've got an aromatic ring, right? Oops. Aromatic ring, oh, like that. And then you have a CH3. Does anybody recognize this group that I have here written in red? So this is, it would be like O something. So it's like this part here. It's like CH3, CH2O. So that would be a toluene sulfonyl, right? Because this is toluene and this is a sulfonyl. So that's an OTS group. So OTS, that's what this is here. That's a tosylate shown here. And so this is the only thing here that's got a good leaving group. And so the SN2 for D is perfectly reasonable, right? Because a tosylate is a great leaving group. So what they have written here, this is OTS minus. Now, if you're going, well, how would I know, you know, what if I didn't recognize that as a tosylate? Well, in that case, I would just look at each one of these leaving groups. I would compare this, oops, where's my green highlighter? I would compare this leaving group to this leaving group to this leaving group to this leaving group. And I would say, which one of these would make the best leaving group? Well, in the first three, you have the negative charge on one atom, whereas in D, you have something where it's got a negative charge, but that negative charge is going to be delocalized, oops, up to this oxygen and this oxygen as well. So it's the most stable of all of them. It's the best leaving group. Anyhow, that's probably the best way I can think of to solve that one. All right, here's another one. Does anybody recognize D? Could anybody tell me what D is? Something our textbook doesn't use a ton of. Brings it up once in a while.
Is that denatured hydrogen or whatever?
Yeah, it's deuterium. Yeah, absolutely. So this is a deuterium. So deuterium is nothing more than a hydrogen that's got a neutron in the nucleus. So it's hydrogen 2. That's all it is. Okay, so we're used to dealing with hydrogen 1, which is called protium technically, but this is just deuterium. And so deuterium technically has a precedence over hydrogen. Like, let's say you saw this on a stereo center, D would come just above hydrogen, okay, and before helium, but you're never going to see helium on a stereo center anyway. But anyhow, that's the whole idea. And idea, get it? Anyhow, and the reason why they love to put deuterium in these questions is just a substitution for hydrogen, but it enables the test writer to test you on your knowledge of a lot of times stereo selectivity and regio selectivity. That's what they're trying to do here. So what they're getting at with this reaction is this. You're taking this epoxide. Okay, so we did a whole chapter where we dealt with, you know, epoxides and ethers and stuff. And they're saying you're treating that with lithium aluminum hydride. So if you have lithium aluminum hydride, and I'm just going to draw the aluminum hydride anion. There we go. So this is going to act as a nucleophile, right? Now, it can either attack this carbon of the epoxide or it can attack this carbon. But remember, it's going to attack the least hindered carbon. On this side, you've got a methyl, and on this side, you've got a deuterium. So obviously, it's going to go to the side of the deuterium because that's smaller. Now the question is the hydride going to go from the top face of this, or is it going to attack from the bottom face of this? Well, it's going to go to the least hindered side. What's more hindered? The side that has a little old deuterium, on it or the side that's got an epoxide on it? Well, deuterium is much, much, much smaller than an oxygen, which is in the second period. Therefore, the hydride is going to come in on the least hindered carbon and on the least hindered face. It comes in from here, which causes the epoxide to open up. But since it's coming from top side, we'll just put here top side attack. And this is the most interesting part, is that when it does that, it attacks this carbon, but it pushes the deuterium down, right? It breaks this bond, but it pushes the deuterium down so that what you end up with, just bear with me here, is something that looks like this. Here's your 6-membered ring. You didn't touch this methyl. It's still going up. Now you've got the oxygen going down like this. Okay, you've got the deuterium, which is now going down because you pushed it down with the hydride, and the hydrogen is going to be pointing straight up like that. So that's the answer to the first step. The second step is just treating it with aqueous acid. So when you treat it with aqueous acid, what that does is it protonates this oxygen so that you end up with OH. So the answer is, which one of these is the right answer? It's this one here. A lot of dots to connect in this question, but if you remember in the epoxides chapter, which would have been, sugar, it's chapter, ethers and epoxides is chapter 13. So in that chapter, chapter 13, it talks about the ring opening of epoxides using a nucleophile. And nucleophiles always go for the least hindered carbon and will attack from the least hindered face. Okay, so if it's something that you want to review, that would be chapter 13. Now, a question I have in my notes here that students have asked me, when we look at this question in the, last week of school, students will ask me, well, Mr. Dion, when is it that the nucleophile attacks the most hindered carbon? Because I thought you showed me that. The only time you see a nucleophile attacking the most hindered carbon is something different than this. It's when you're doing an acid catalyzed ring opening. So it's when you have an oxonium, but it's protonated like this, okay? Then this is a tertiary carbon here. It's only in that case that if you have a nucleophile, okay, then in that case, it can attack the most hindered carbon, okay? So this is acid catalyzed epoxide opening. We'll just put here ring opening. All right, so if you need to look that up, you can take a look at those rules again, but that's kind of one of the most interesting rules with epoxide opening, is that if it is acid catalyzed, it will attack the most hindered carbon. It's kind of almost like it's not an exception, because I provide you with a rationale when we did the chapter, but it's just one of those things that you kind of have to be on your guard looking for. Okay, let's take a look at question 12. This is nothing more than looking at transition states. I mean, this goes all the way back to Gen Chem 2 in the kinetics chapter of General Chemistry 2, and then chapter 6 in Organic Chemistry 1, and then all these transition states that we ever looked at after that. But which of these is best depicts the transition state for the reaction with potassium methoxide and iodomethane? I mean, come on, that's the most basic SN2 reaction that you could possibly have. So you're going to have your alkoxide like this, and it is going to do a nucleophilic attack, loss of leaving group, and you're done. Well, if you look at A, it's missing an oxygen in here, so that's not right. If you look at B, I don't even know what KO is. I'm not really sure what somebody was doing there. And if you look at D, I mean, this is just flipped around backwards, and I really have no idea how could you have a hydrogen with 2 bonds? I mean, that's a double no. But if you look at C, you can see in C that it shows, they're trying to show the molecular geometry of the carbon, because you've got a hydrogen going in back, and then you've got one coming in front like this, right? And it's like it's almost being kind of, trigonal bipyramidal for a second there while the bond is being formed and bond is being broken. So this would be the transition state, and this is just an SN2 transition state. So that would be all the way back in chapter 7 of Organic Chemistry 1. Okay, this comes from the alcohols and ethers chapter. This would be a chapter 12 question. So let's see here. Could anybody predict? I'll let you take a look at the answers. Could anybody predict what the right answer for this one is? We got a whole holy host of answers here. There's only one of them that's right, though.
Is it A?
I don't think it's A. I think you're in the right vein, though, for sure. So this goes back to this reaction where we looked at R, O, we'll put R prime like this. If you treat that with excess HBr and cook it up, you end up with R, Br, and R prime Br, as long as the R groups are not aromatic. Okay, so since this isn't an aromatic carbon, this isn't an aromatic carbon, and this isn't an aromatic carbon, all those bonds end up being to bromine. So the answer is B. The red carbon is now bound to a bromine atom. The blue carbon is bound to a bromine atom, and the green carbon is bound to a bromine atom. So put in another way, this is a question I asked you on the quiz, was let's say you have an aromatic compound like this, okay, and you treat this with excess HBr. What you end up with is the phenol, because you can't get an SN2 reaction at an sp2 hybridized carbon, and then you'd end up with methyl bromide. Okay, so again, that's a chapter 12 question, so make sure you review chapter 12. Just the acidic cleavage of an ether is what you would call this. So acidic cleavage of an ether. That's all that's going on here. Nothing more than that. Oh boy. Question 14. Identify possible products of dehydrohalogenation of trans 1-bromo, 2-methyl, cyclohexane. I think we're going to need to go over to a blank document for this one. Just bear with me while I scribble this question down, because there's a couple of concepts that I want to go over with you here. Things you want to be aware of. So let's see here. We have this compound. So we have a 6-membered ring, and they just give us a Haworth projection like this, where you have a hydrogen going up like this. Then you have the methyl group going down like that. Then you have the bromine coming up like this. And you have a hydrogen going down like that. And it says you're doing a dehydrohalogenation with KOH. So what does dehydrohalogenation mean? Hydro stands for hydrogen, so you're losing hydrogen, and the halogen, the only halogen in here is bromine. So you're losing HBr. So in order for us to eliminate this bromine, could anybody tell me what the requirement is for a hydrogen with respect to its relationship to that bromine? I'll give you a clue. There's a word that I taught you in Organic Chemistry 1, which was anti-something. Does anybody remember that word?
Anti-periplanar.
Yeah, it's anti-periplanar. So what that means is, like, let's say you had a chair, right? And this is a chair. So if the bromine is going up and is axial, that means this methyl is going down and is axial, right? So I've got a proton here, and I've got a proton going here. But is this proton, so this proton that's going up is up and axial. Is that proton anti-periplanar to the bromine? No, not even close. Is there a proton anti-periplanar to the bromine? Like, what if I draw a proton in here and this proton down here? I'm kind of running out of space. Are either of those protons anti-periplanar to the bromine? The green one is anti-periplanar to it. So if we highlight the bromine and this proton, they're anti-periplanar. Look, you could look at it this way too. if the bromine is up and axial, that means that this proton is up and equatorial. So you cannot do an elimination. You cannot form a double bond here. It's impossible. But if you draw these two protons in, so if I draw the bromine going up, or the hydrogen going up, and then I draw a hydrogen going down like this, if the bromine is up and axial, that would mean that this hydrogen is down and axial. So I can form a double bond here. Therefore, after the elimination, the only possible thing that I could have would be something with a double bond here, and then I've still got this methyl group that looks like that. So I'm going to see if I can copy and paste that into another document. So copy. Let's go back to the quiz. Hope this works. So we end up, let's see. There we go. So that's what we drew. Is there anything in these answers here that looks like what we've drawn? Now they haven't put any stereocenters in here. But is there anything in here that looks like what I drew? What's the closest thing to what I drew in here? Absolutely, it's A, isn't it? Right? They just left out the stereocenter. That's all. So, and that's the only thing that we could make. You can't make this compound, that one. Well, these are all the same. You can't make that. You can't make this. This is the only thing you can make, which is this or this. But you can't make this, so the answer must be A. And there we have it. Boom. Just like that. The answer is A. All right. Give me a thumbs up if you follow me on that one. The whole concept of anti-periplanar. I mean, that's something we haven't looked at in a while. But I know, again, that many of my students are interested in standardized exams. Let's try one more. Take a short break. Let's hear. Which molecule will correctly complete the reaction shown? So this is a methyl ketone. A methyl ketone. And I'm doing something with water, sulfuric acid, and mercuric sulfate. So this is mercuric sulfate. The only time you ever would have seen mercuric sulfate in this class is in chapter 9. So this is chapter 9, which is alkynes. And that kind of gives away the answer because there's only one compound here that's an alkyne. I kind of cut the bottom off here, but it's this compound that's an alkyne. So what happens is when you take that alkyne and you treat it with water, sulfuric acid, and mercuric sulfate, you do the Markovnikov addition of water across the triple bond, and you end up with this. Ah, shit, my finger's in the way there. So you end up with this, which is an enol, but that enol undergoes tautomerization. I'm kind of running out of space here. It undergoes tautomerization to give you a methyl ketone. So again, this is Markovnikov addition of H2O on a terminal alkyne. All right, why don't we take a short break? And I'd like everybody to try to do as many questions as they can, starting at question 16. If you haven't done any, I mean, give as many a shot as you can. And if you have, well, we'll come back soon and we'll take a look at these. So if you look at the first one, 16, you can see that it involves Diels-Alder chemistry. So Diels-Alder chemistry, that would fall under the umbrella of chapter 8. No, it would be chapter 16. Yeah, I was right. So this would be a chapter 16 thing, Diels-Alder. And then, well, the next one, 17, that's, you can see that you've got a triphenylphosphine in here. So when you have C6H5, that's condensed form for a phenyl, or C6, C6, that looks worse. There we go, C6H5. It's just a phenyl. So that means that number 2 is triphenylphosphine. Therefore, this must be a Wittig reaction. So something you could try to take a look at.